In this video, we're going to talk about something that used to be in this textbook version, but not anymore. So I guess the textbook we have now is a combined C++ and data structures book. And it used to, and before, I keep saying it used to be, the previous version had a separate book on data structures. And one thing that the other book covered, which I think is important for us to cover, is the idea of self-balancing trees, okay? So the issue with this comes if you were to, for example, do a binary search tree of the numbers 1 to 20, okay? Because of the way the binary search tree works, 1 would be the root, 2 would be its right child, 3 would be its right child, and so forth, all the way until the 20, okay? So you'd end up with 19 levels, okay? And if you were to search for a number in that list, you would have no advantage at all over a linked list or anything else, right? You would have to go sequential because it was not structured correctly. So there's this idea then that we could create trees that as you're adding elements will reconfigure themselves in order to be able to stay balanced to some degree, okay? So I've popped up here the old textbook, and we'll kind of go through this, and you'll have this video to look through it if you need to, okay? So again, it's a special type of a binary search tree called an AVL tree. The AVL comes from the mathematicians who kind of came up with this idea, okay? So we first define a perfectly balanced tree where the number of left and right subtrees of the root are equal, okay? And the left and right subtrees are also perfectly balanced trees. We've seen this recursive definition before with trees, okay? So you're not likely to ever get a perfectly balanced tree, okay? So instead, we're going to come up with this AVL tree that's going to say that the height of the left and the right subtrees of the root differ by at most 1, okay? So you can have it be off by 1, okay, one way or the other, okay, but no more than that. And also that the left and right subtrees, of course, are also themselves AVL trees. So we have an example here of some trees that are AVL trees. Okay, so if you look at all of these, at no point is there more of a difference between left and right than 1. Okay, so over here, these are not AVL trees. So this node has 2 as a height here, but 0 on that side. Okay, and this one would have a right child of 2, a left child of 0, and so forth. Okay. So that's how that's going to work here. So here's the proposition for us. If T is an AVL tree and X is some node in tree, then the XH minus the XL, okay? So that's the balancing factor we're going to talk about. So XL, sorry, is the height of the left tree. I've lost my way here. It should be XL is the left, and they're using XH for right. That's weird. Okay, not using XR. Okay, so this is the left minus the right. Okay, so since T is an AVL tree, then X is some node, then this difference is less than or equal to 1, and that's the absolute value of this, which makes sense. Okay, so if we have a node in the tree, if it turns out that the left is more than the right, okay, so there are more, the height of the left is greater than the height of the right, we say that's left high. If it's equal, we'll say it's equal high. If it's greater, if the right is greater, we say that it's right high, okay? But no more than by 1, okay? Just because it's an AVL tree. So the balance factor that we can create then is going to be defined by, okay, the right minus the left, the height of the right minus the height of the left for each node. Okay, so if it's left high, since it's right minus left, we have a balance factor of -1. If they're equal height, 0. If it's right high, we have a factor of 1. Okay, so we would say that any node X will violate the balance criteria if this absolute value of the difference between the left and right children is greater than 1. Okay, so in order to keep that from happening, we're going to have to modify our node. Okay. So an AVL is a binary search tree. Okay. But we're going to change the node to include not only the info, which we had before, not only the left link and right link pointers, which we've had before. Okay. These are not node types anymore. These are AVL nodes. Okay. And this book uses the Elm type instead of the type, I think is what the other book uses, the newer book. Okay. But what we're adding here is this B factor, which is an integer. That's going to be the balance factor. Okay. And because our AVL tree is a binary search tree, then the search is going to work exactly the same. Search doesn't matter. Okay. Other things such as finding the height, determining the number of nodes, whether the tree is empty, traversal, all that. All those are exactly like the binary search trees. Okay. However, insertion, we have to insert in the proper place. And we have to rebalance the tree if necessary, are different, as is deletion. Okay. Because after you insert or delete, you still have to have an AVL tree. Okay. So the first thing that they start with here, and the code that's in the book, I will put out into the temp file. It's not a complete program. That's what you're going to work on, but I will have the parts here. Okay. So if you're going to insert an AVL tree, you first have to find where it would go normally as part of the binary search tree. Okay. So once you've done that, okay, you insert the tree, you have to figure out whether or not you still have an AVL tree. Okay. So you start by traveling the same path back to the root. Okay. And make sure if the balance factor's changed, they're okay. Okay. They're still okay. So here's an example. We have the tree that has a root of 50. We have a 40 and a 70. We have an 80 down here. Okay. So this one is right high. Okay. It would have a balance factor of 1. There's 2 right minus 1 left. So that's a 1. This one also has a right high of 1. It's 1 minus 0. This one is equal 0, 0. Okay. If we were to insert an 80 here, sorry, a 90, the 90 would go to here, 1 more. Okay. Now we have trouble because while the 90 is equal, okay, the 80 is actually right high. They show an equal there, which it's not. Okay. I guess that's what it was before. We haven't calculated that one yet. And this one is going to be, it's going to violate. Okay. This one's going to have a 2 minus 0. We can't have a 2. Okay. So if we were to reorient it in this way, okay, to where the 70 moves down and we pull the 80 up, we're now back to balance. Okay. And that's kind of the idea. Okay. So here's another example. Okay. And we had the same tree, but we're inserting a 75. 75 goes over here. Okay. This one, we're going to have 2 changes. Okay. We have to start by moving the 75 to the right. So move it up and the 80 over. We then have to rotate left with the 70 to come down to give us this structure. Okay. So lots going on here. Okay. And here's another where we're inserting into a more complicated tree. So you can see the flow as it goes through. It's not in violation. Now it's in violation. And we have to modify things in order to make things work out. Okay. So there's one more case they give us here, but in general, we're now going to go through the ways we're going to do these rotations. Okay. So the rotations come in 4 varieties. There's a left, rotation, right rotation, a left, right, and a right, left. The simplest ones are the left and the right. Okay. So we have this little figure here. We have root. We have the P over here. Okay. We have 2 subtrees here, T1, T2, and a subtree here, T3. Okay. So we're going to look at a rotate, okay, in order to move the A up and the B down in order to make the trees work differently. Okay. Okay, so we note the things about this tree because it's a binary tree. Every key in Ti or T1 is greater than the key in node A. Every key in T2 is larger than the key in node A, and every key in the subtree T2 is smaller than the key in node B, okay, because of where it follows, okay? So therefore, if we make T2 the right subtree of node A, the left subtree of node B, we make node B the right child of node A. Node A becomes the root of the reconstructed tree, okay? Okay, so let's look now at the actual rotations. And there's more pictures here you can look through, but here is the rotate to left, what's really going on here, okay? So we're going to send to the function rotate to left a node, okay? It's root of the node we're sending, okay? A pointer to a root, okay? Then we're going to create another pointer to an AVL node called P, okay? If root is equal to null, we've got a problem. We've been using null PTR, but NULL in all capital letters is the same thing, okay? This is an older version. It does still work. I compiled it, okay? There's an error in the tree, okay, that you can't really have that, okay? If we're doing a rotate to left, so if the R length of root is null, then there's no right tree to rotate. You can't rotate nothing, okay? And where it's okay is down here. So this is where we want things to actually happen, okay? So in this case, we do have a right one. We wouldn't be sent here unless we thought we needed it. So we're not dealing with the balance factors yet. This is doing the task once we've determined that needs to be done, okay? So we're letting P equal to the right length. So we've got this pointer P that was pointing to root, okay? We're now going to, no, we're going to set it to the, sorry, we haven't set it to anything yet. We're going to set it to the right length, okay? And then we're letting the root R length be equal to the P's left length, okay? So the left subtree of P will become the right subtree of root, okay? And then we're going to make P the new root, okay? And this, if you would sketch it out on paper, has the effect of the rotation that you're talking about, okay? In a similar vein, if we decide we have to rotate to the right, okay, we're again going to create this pointer P, okay? And again, if root's null, there's an issue, or if now the left root's null, there's an issue. If not, we're going to do the opposite of what we did before. So the right tree of P becomes the left subtree of the root, then we're going to make P the new root, okay? So once we have these rotations, the next thing they're going to create are these balance from left and balance from right, which are used to reconstruct the tree at some node, okay? So the pointer of the node where the reconstruction occurs is passed as a parameter, and the function then will use the rotate to left to rotate to right to fix the tree, okay? And also adjust the balance factors, all that stuff, okay? So this balance from left is called when the subtree is left double high, okay, and certain nodes need to be moved to the right subtree. The balance from right is going to be just the opposite of that, okay? So this balance from left, again, takes a node. We have two pointers here, P and W, okay? P is going to point to the left subtree of root, okay? Then we're going to switch. So P is this left subtree of the root. We're going to look at its B factor. B factor is in the node, so it should always be there, okay? Since it's an AVL tree, there are always three possibilities. It's either equal to -1, 0, or 1, okay? So if it's equal to -1, okay, that means that it itself is left heavy. The left link is left heavy, okay? So we're going to set the root factor to 0, because it's going to be here in a minute. We're going to set the B factor of P to 0. We're then going to rotate, and we're done. We've reset the factors, we fix stuff, we're good, okay? If the case is 0, if we're balanced, then we can't balance from the left. There's nothing to balance from. Okay. If the case is 1, which means we're right heavy, okay, then we're going to set W to be the right length and then basically do the same thing we did before. Okay. So this switch and this switch are the same thing, switching sides. Okay. So again, it could be -1, it could be 0, it could be 1. Okay. So, and that gets us down to the switch that we do at the end. Okay. So that's balancing from the left. There's balance from the right that does the same idea there. Okay. So once you have that, then it's a matter of figuring out how the insert into AVL is going to work. Okay. It's going to insert a new item into the tree. Okay. So it's got to make sure it goes to the right spot. Okay. So the steps, first one's pretty straightforward, like always. We're going to create a new node. Okay. The AVL node. We're going to copy whatever information is going to be inserted into this new node. Okay. We then have to search the tree and place it just like we would do normally. Okay. So this is going to look just like the code for the binary search tree. When you find the spot that you need to insert it, you insert the new node into the tree. Okay. You then have to backtrack along the path, okay, to find this new place, all the way back to the root node. Okay. And you're checking the balance factors along the way. They're the only ones that could be affected. Okay. And you're reconstructing the tree if necessary. Okay. So the easiest way to implement this, because of this whole backtracking thing, is to use recursion. Okay, which is what we're going to do here. Recursion allows us to close out and go back to the previous node. If not, we would have to do something crazy. Okay, put it on a stack, or like we did in class the other day, yesterday, it seems. Okay, so this insert into AVL then is going to take a node, and it's going to take. Okay, we've gone into something else here. So this takes. I love when you don't lose your way until you lose your way. Okay, the item to be inserted and the pointer node of the AVL tree are passed. Okay, insert into AVL. They haven't mentioned this is taller or not yet, so we'll have to come back to that. Okay, yeah, there's the new node we're creating, and there's the root node. Okay, so if the root node's equal to null, there's nothing in the tree. We're going to add the root's going to be the new node is taller is equal to true. Okay. Then we have to look at the root info, compare it to the new node info. Okay. We assume that when the new node was created, the info was put onto that. Okay. If that's the case, if they're equal, then there's no duplicates that are allowed, so we can't do that. Okay. Else if it's greater than, okay, if the root is greater than the info, then the info smaller is going to go to the left. So we're going to again insert that into the link, the R link. Okay, sorry, L link. It's smaller. We're going to insert it, call it recursively to build the next layer. We're sending along the is taller as we go. Okay, the is taller was sent in to begin with. Okay. If is taller, so after insertion, the subtree grew. So the is taller now, that's what it's doing. It's seeing, was there a change? If so, then we have to recalculate things. Okay. If it's true, we're going to do the switch. If not, there's nothing to change. But if it switched, okay, then it's going to either be a -1, it's going to be a 0, it's going to be a 1. Okay. And if it's a -1, we're going to balance some left on the root. Okay. Is taller is false before we hit our break. If the case is 0, then the B factor for root will be -1, is taller is true, and we break. Case is 1, then the B factor is equal to 0 and is taller is false. Okay. So the else here goes back to here, that if it's not is taller. Okay, then we're going to go ahead and insert here. That ends the if. Is that the if we're dealing with? Yes. Okay. Then we're going to insert into the R link, the new node. Those are the options. Okay. So up here, we're inserting into left link. Down here, we're inserting it into R link. Okay. And again, we're setting along this taller. Again, we're checking to see after insertion, did the tree grow? If it did, then we're going to balance it based on this as before. Okay. But this time, if it's a 1, then we balance from right. Okay. Here's an example of this. We start by inserting a 40. We insert a 30, it goes there. This was equal. Now this shows this is equal, but that is left. A new node is always equal, so the balance factor is always 0. We're going to insert a 20, get to here. Okay. We now have to do a rotate right to get us to here. We're now back to equal. Okay. We insert a 60. 60 is going to go here. Okay. It's equal. That's equal. That's right. That's right. We're okay. This one we insert a 50. Now we're not equal. Okay. So we're going to do a right left rotation here. We would start with the right rotation. The right rotation will pull the 50 up and the 60 down to there. Okay. We then do the left notation, which will pull the 50 up again with the 40 to the left and the 60 to the right. Okay. And so forth as we go all the way through this tree. Okay. And we have the two-step process. If you have a straight line with too many, so if you have a straight line with 3 nodes in a straight line, basically, okay, and that's out of balance, then you just do a left or right rotation. But when you have the dog leg, and when it goes, right, left, like we see with the 40, 60, 50, that's when you have to first convert it into the stick by moving up the 50. Okay. And then you would go from there. Okay. Probably worth, let me see if I can try to draw a picture. You know that we all love my pictures. Okay. Just because the book does it in one step, let's make sure that we can see what's happening. Okay. So in the position they had, go ahead and draw some circles here. So we have to deal with that issue. Let's see, there are 1, 2, 3, 4, 5. So there's 1 there, 1 there, 1 there, 1 there, and 1 there. Okay, that's only right. 30, it's not big enough, but you get the idea. Let's just do that as it's too many. Can I make these bigger? And you can't edit them, which is unfortunate. So anyway, so this is 30, this is 20, this is 40. So I'll go ahead and put a 40 there, and it looks ugly, but you get the idea. Okay, this is a 60, it'll be even uglier. And this is a 50. Okay, as it stands, I might as well finish on out here. So this is a 30. Oh, let me do that. Did it way over there. Don't know why. And this is a 20, which we don't care about at the moment. Okay. So the lines that we have here are from the 30 to the 40, from the 30 to the 20, the 40 goes to the 60 goes to the 50. Okay. So the balance factor at root is going to be 1, 2, 3 minus 1. Okay. Or a balance factor of 2, which is too many. Okay. So our first transformation here has to be to get this into a stick. So we're looking at this and we're doing a right rotation here. Okay. So that when we're done, I'll try it's bigger this time. That's the wrong shape. There we go. When we're done, the 40 will still be up here. Okay. But the 40 now, we're rotating right. So that's going to go into the 50. Which will now go into the 60. Okay, so that's, let me get this, 50, 60. Okay, so we haven't solved our problem in that we still have the same number, we're still out of balance, okay? And then this goes, of course, up into here and here. So there's still one above, 2, 3, and one over here, and we're 2, which is fine, okay? And just to make sure we're clear, if I let me erase that. So we can figure out where we are. Okay, so this is after we've made that first rotation. Okay, and we've got 30 was up there, our 20 was over there. 30 there, 20 there. Okay. That goes there, that goes there. Okay. So we still have our balance factor, our B factor is still a 2. Okay. So that didn't help that any. But it now allows us, we did a right rotation to get here. We can now do a left rotation. Okay. And the left rotation is just going to move the 40. I don't think I can do that anymore. No. Can I? No, let me change that. Anyway, we're going to basically move the 50 up to where the 40 is. The 40 goes over here. The 60 goes over there. Okay. And once we've done that, then we'll have 2 on this side, 1 on that side, and we'll still be okay. Okay. Not sure if that helped. Wish I had the ability to, draw like a normal person, but I can't. Okay. So that's how the rotations work. Okay. So the rotate left, rotate right are the single rotations. The rotate from left and from right are the 2 rotations, the right, left, and left, right. Okay. So that's the basic idea there. Okay. And they go through all that in detail. Okay. So we also just need to have a simpler, this is kind of what was missing from before. We have a function to call this. So the insert function then is the one that creates the new node, that sets the initial is tall or equal to false, okay, adds the info over, okay, sets the L link, R link to null, and sets the B factor to 0, and then inserts all of that into the tree, okay? And the reason we have this, I call this a wrapper function, because someone using it's just going to want to insert a 5. They're not going to want to have to insert whether it's taller or not. They won't know what that means. Okay, so that's why we're making this simpler. Okay, so this is where it gets what I want you to work on. Okay, and again, all the code that's in the book here, I've copied over, or I will copy over to the TMP file. Okay, it's called AVL Tree Type, I think, AVL something. It's in temp. Okay, so what I want you to work on here is to design the class to implement this AVL tree as an abstract data type. Okay. The node structure is different than a binary search tree. We have an extra thing. We have the B factor. So we can't directly derive it from the class binary tree type. Okay. So we're going to have to find a different way to do that. Okay. And we'll see how that goes. There's a section here on deletions. We may worry about deletions, but maybe not. We'll see. So for now, just work on the insertion part, getting it to where you can insert. Okay. And again, you can copy over big chunks of the binary search tree, because pretty much you'll have to change the node name from node type to AVL node, but all of the height and all the other stuff should work properly. Okay. And you'll use the tree height when you're calculating the balance factor, although it kind of does it internally a different way. So yeah, you don't have to do that, I don't think. Okay. Anyway, that's what we're going to work on.